Today we are going to talk about a hidden battle happening inside your plant every single second. The intersection of a massive iron infrastructure and a microscopic life living with your cooling water. So we are exploring how to manage microbiologically influenced corrosion or MIC using a combination of a smart sensing and a breakthrough biohacking approach using D-amino acids. So look at the main graphics here. It shows a styled blast furnace, but notice the glowing neural-like overlay on the right that represent the biological ecosystem that lives inside your cooling circuit. An ecosystem that can either protect or destroy your assets. By the end of this session, you will understand how to move from brute force chemistry to a surgical data driven strategy for plant integrity. To understand why this matters, we first have to look at the sheer scale of the challenge. So, now coming to the scale in steel making. So, this slide illustrates what I call the paradox of scale. On the left, you see the blast furnace representing tens of millions of dollars in infrastructure circulating 75,000 gallon of water for every single ton of steel produced at temperature over 2000 degrees centigrade. But now look at the right side of the screen. That's the threat. It's a layer of invisible microorganism, only 20 micron thick. Only 20 micron thick. To put that in perspective, that's thinner than a human hair, yet it accounts for 20% of global corrosion cost and can reduce your heat transfer efficiency by 7%, which is a very impactful figure. We can no longer bridge this gap with run to fail maintenance. We need molecular level intervention. So, before we tackle the biology, let's look at the thermal armor these microorganisms are trying to penetrate. Optimizing blast furnace steps. How? So this chart breaks down the three main type of steps we use to keep the furnace from melting. On the left we have a copper strips used in high heat zones like the Bosch and the Bailey because they have maximum conductivity. In the middle you see the cast iron strips which are lower cost and highly abrasion resistance for the hearth and upper stack. Finally, on the right, we have steel strips for transition zone. Each of these material react differently to water chemistry and microbial growth. So, if our cooling water is not optimized, these expensive components become vulnerable to localized heating and failure. The water doesn't just cool the staves, it also powers the gas cleaning process. So the pressure temperature cascade, as you can see. So let's trace the journey of the gas. Look at the line graph moving from left to right. We start with a raw top gas at 600 degrees centigrade, drop through the primary cyclone where gravity removes the big dust particle. Then it sits the wet scrubber where atomized water brings the temperature down to about 70 degrees centigrade. By the time the gas is clean and ready for the turbine, it's down to 40 degrees centigrade. So notice that 70 degrees centigrade mark in the scrubber, that is the sweet spot where the specific heat loving bacteria thrive. Leading us to our next concept. To manage this temperature, we have to treat the plant water as a complete ecosystem. So the industrial water ecosystem, this target graphic shows the different type of water we manage. The bright blue center is our soft water or closed loop system. This is the lifeblood of the furnace cooling wall and tuyeres with a 99.95% circulation rate. Moving outward, we have a purified and demineralized water for boilers and then direct flow water for gas cleaning and slag granulation. That outer ring carries massive thermal load and up to 1500 of suspended solid. How do we keep all these different circuits clean when they are constantly under biological attack? That brings us to our primary antagonist, MIC. So now coming to our invisible threat, that is MIC or microbiologically influenced corrosion. So look at this cutaway of a pipe. That glowing green slime inside is not just gunk, it's a living chemical factory. The main culprit here is the sulfate reducing bacteria or SRB. This is called sulfate reducing bacteria. So these anaerobic organisms love the low flow 70 degrees centigrade area of your circuit. Here is their three-step attack. First, they breathe sulfate from the water. Second, they metabolize into highly corrosive hydrogen sulfide right against the metal. And third, that sulfide react with your carbon steel to cause deep localized pitting and cracking. This is why MIC is responsible for a full fifth of all corrosion costs globally. And the damage is not just physical corrosion, it also a literal barrier to cooling. So it has got a effect, manifold effect. Coming to the insulating effect of biofilm. Biofilm is the 97% water, but its structure is actually more insulating than mineral scale. So look at the table on the slide. At just 20 micron, invisible to the naked eye, you lose 7% of your heat transfer. 7% of heat transfer if gets affected, then efficiency of cooling will affect and consequently damage to the cooling system it starts. Uh, so we have to follow the red warning bar at the bottom. Once that layer hits 100 micron, you are in critical zone. This is where you face cooling panel failures or worst steam explosion in the electric arc furnaces and many more. So you cannot wait until you see the problem to fix it. So why cannot we just dump more bleach or biocide in the water and call it a day? So it is a very important question. So while traditional biocides fail, this diagram shows why brute force chemical dosing fails. The bacteria secrete what's called an EPS matrix, a fortress of amyloid fibers and polysaccharides. The sessile bacteria anchored in this slime are up to 100 times more resilient to biocides than free floating bacteria. So, if you just increase the doses, you create three new problems. You accelerate the chemical corrosion of your own equipment, number one. You risk environmental discharge violation, and you leave behind persistent cells that repopulate the system even faster. We need a way to unlock the fortress rather than trying to blow it down. So, D-amino acid biohacking, this is the biohacking breakthrough. Look at the transition from left box to the right box. On the left, you see the fortress held together by amyloid fiber. We introduce D-amino acid, the molecular keys you see in the right hand image. These D-amino acid replace the D-alkaline in the bacterial cell wall, which causes the structural scaffold to collapse. It sends a signal to scatter, forcing the bacteria to abandon the biofilm and return to a vulnerable, free floating state. We are not killing them yet, we are just making them homeless. Once they are homeless, we can use much less chemistry to get the job done. So, this is our next slide, which is about the synergistic enhancement, that is doing more with less. So, look at this bar chart. The red bar shows a high dose of traditional biocide, which is effective but expensive and corrosive. Now, look at the teal bar on the far right. By using D8 mixture, a cocktail of 8 specific D-amino acid, we can reduce our traditional biocide doses by 50% while achieving identical or even superior results. D-amino acids are not biocides, they are enhancer that unlock the matrix so our existing tools can actually reach the target. To make this work, however, we need to know exactly when and where to dose, and which is supposed to be very important. So, coming to the real time visibility in the environment, we cannot manage what we cannot see. So, this slide shows the three sensors that give us real time eyes inside the pipes. On the left is the Pyrexis LT635, which uses a mechanical wiper to manage up to 30,000 ppm of suspended solid. In the middle, in the Solenis on guard 3B, it uses ultrasonic pulses to calculate the exact fouling factor in real time with 5 micron resolution. And on the right, the ALVIM sensor detects the electrochemical activity of bacteria the moment they settle, giving us an early warning before the biofilm even forms. Now let's put it all together into a single automated system. The closed loop, a smart ecosystem. This is our immune system for the plant. It's a 4-step loop. First, we detect using our LVIM and on guard sensors. Second, we signal by triggering a microdose of the D8 amino acid mixture to break up any settling bacteria. Third, we eradicate with a low dose of target biocide like THPS to flush the free floating cells. Finally, we verify the water quality using Pyxis analytics. The core insight here is that we no longer treat water as a passive coolant, but as a highly active, living biological system. This shift changes everything about how we maintain our plants. Now, coming to the redefining the heavy industry maintenance. To wrap up, I want to leave you with three takeaways. First, run to fail is obsolete when you are protecting tens of millions in thermal armor. You have to detect threats at the 5 micron scale. Second, nature mimicking chemistry is the future, replacing chemical warfare with the molecular signaling cuts biocide use by half. And third, data bridges the gap, integrating sensor with your plant void system transform blind spot into predictive control. Efficiency in the blast furnace begins not with the steel but with mastering the microscopic ecosystem of the water that cools it.